Have you ever wondered how a Tau program is written and executed? Tau, a programming language deeply rooted in Boolean algebras and temporal logic, offers an intriguing approach to defining and executing software. Let's embark on a journey to understand how a Tau program comes to life, starting with the concept of a program specification. A program specification, in essence, is a formal description of what the program is intended to accomplish. Imagine we're building a simple program that, at each time step, takes two input numbers, adds them, and outputs the sum. In the world of Tau, we would translate this into a logical formula that encapsulates the desired behavior of this program over time. Let's visualize this with two input variables, x and y, and an output variable, z. Our specification could be represented by the formula z underscore t equals x underscore t plus y underscore t, where t signifies a discrete time step. Even though Tau primarily works with Boolean operations and numerical ones are turned into logical operations, we'll stick with this arithmetic representation for the sake of simplicity. After we've laid out our program specification, the next step is to transform it into a logical formula that Tau can work with. This entails encoding our arithmetic operation into a Boolean function. We won't delve into the intricate details of this encoding process right now. Let's just assume we've got a Boolean function f(x,y,z) that accurately represents our addition operation within the realm of Boolean algebras. For Tau to execute the program, it needs to locate a satisfying model for the formula provided the inputs at each time step. Essentially, given values for x and y, Tau needs to find a value for z such that f(x,y,z) is true. In layman's terms, this involves searching through the possible values of z until one is found that fulfills the condition set by f. Now that we understand what a program specification is, let's dive into how it transforms into a logical formula. In the world of Tau, program specifications transform into logical formulas. Imagine a simple program that receives two inputs, adds them, and outputs the sum. This is our program specification, a formal description of what it's supposed to do. But how does this specification translate to the language of Tau? Let's start by identifying our variables. We have two input variables, x and y, and an output variable, z. Now we can represent this specification with the formula z sub t equals x sub t plus y sub t, where t stands for a discrete time step. This formula is a simple way of saying that at each time step, our program should output the sum of the two inputs it receives. However, Tau language is rooted in Boolean algebras and temporal logic. It doesn't deal with arithmetic in the same way we do. Instead, it abstracts numerical operations into logical operations. So, how do we transform our arithmetic representation into a logical formula that Tau can understand? Let's abstract away the details of this transformation for now. Instead, let's assume we've got a Boolean function. Let's call it f, that correctly represents our addition operation. This function takes our variables x, y, and z as inputs and represents the logical relationship between them. In other words, it's a blueprint that tells Tau how to add our inputs. So, our program specification, which started as an arithmetic operation, has now been transformed into a logical formula. F of x, y, and z. This formula is the heart of our program. It's the rule that Tau will follow to execute each step of the program, from receiving inputs to producing outputs. In this way, the world of Tau programming transforms program specifications into logical formulas, breathing life into abstract ideas with the power of logic. With our program's logical formula in hand, we're ready for the next step in the Tau execution process, finding a satisfying model. Our specification has now transformed into a logical formula. What comes next is finding a satisfying model. Finding a satisfying model is a critical step in executing a Tau program. Once we've transformed our program specification into a logical formula, it's time to find a satisfying model. This is where the magic of Tau programming really comes to life. So, what does it mean to find a satisfying model? In essence, we're looking for an output that makes our logical formula true. Given our inputs, we need to find a value that satisfies the condition imposed by the logical formula. Let's consider our earlier example. We have two input variables, x and y, and an output variable, z. We've already encoded our desired operation, addition in this case, into a Boolean function that Tau can understand. Now, we need to find a value for z that makes our formula true. Think of it like a search mission. We're exploring the space of possible values of z, looking for that golden ticket, the value that satisfies our formula. But this isn't a random search. It's driven by the logic encoded in our Boolean function. The process unfolds in three stages: input reception, computation, and output production. During input reception, our program receives the inputs for X and Y at each time step. These inputs could be anything: numbers, text, data from a sensor. What matters is that they're the raw materials we're working with. Next, we move to computation. This is where the Tau system flexes its muscles. It computes the value for Z that makes our logical formula true. To do this, it evaluates the formula based on the current inputs. And finally, output production. Once the Tau system finds a satisfying value for Z, it presents it as the result of the program at that time step. This could be a simple number, a piece of text, or a complex data structure. Whatever it is, it's the outcome of our program's operation at that particular moment in time. This process repeats at each time step, allowing the program to respond dynamically to the input stream. It's a cycle of receiving inputs, finding satisfying outputs, and producing these outputs. The program is always ready to take in new inputs, crunch them through its logical gears, and produce the corresponding outputs. It's important to recognize that this isn't a one-time process. It's a continuous cycle, with the Tau system constantly receiving new inputs, finding satisfying models, and producing outputs. It's a dynamic system, capable of adjusting its output in response to changes in the input stream. This is one of the key strengths of Tau programming. It's not just about producing a single output, it's about creating a system that can adapt and respond to changes over time. So, that's how we find a satisfying model in Tau programming. It's a search, but one guided by the logic of our program. And at the end of that search, we find a model that satisfies our logical formula, giving us the output we need. With a satisfying model at hand, we are now ready for the execution of our Tau program. The execution stage is where our Tau program comes alive. This is where the magic happens, where the logical blueprint we've constructed springs into action and starts processing data. Let's recall our simple Tau program, which adds 2 numbers at each time step. We've already transformed its specification into a logical formula, and we've found a satisfying model. Now, it's time for execution. Execution in Tau is a cyclical process. It's like a well-tuned machine that keeps churning, processing inputs, and producing outputs at each time step. The cycle comprises 3 main stages: input reception, computation, and output production. In the first stage, input reception, our Tau program receives values for the input variables X and Y at each time step. Remember, these are the numbers we want to add together. It's like the program is opening its eyes at the start of each cycle, ready to take in new information. Next, we move to the computation stage. Here, the Tau system performs a logical evaluation of the formula based on the current inputs. The system is trying to find a value for Z, the output variable, that makes our Boolean function f, x, y, z true. It's like a puzzle solver searching through the space of possible values for Z until it finds the perfect fit. This is where the meat of the computation happens, where the program exerts its logical muscles to solve the problem at hand. Once the system finds a satisfying value for Z, we move on to the final stage, output production. The satisfying value for Z is outputted as the result of the program at that time step. It's like the program is announcing, here's the sum of your numbers. And voila, that's one cycle of the execution process. But the beauty of Tau is that the program doesn't stop here. It continues this cycle at each time step, dynamically responding to the stream of inputs over time. It's like a vigilant sentinel, always ready to process new data and produce the corresponding output. So in essence, the execution of a Tau program is a dance of logic and computation, a rhythmic cycle of input, processing, and output that keeps repeating over time. It's a testament to the elegance and efficiency of Tau, to its ability to handle complex computations in a systematic, step-by-step fashion. But of course, our Tau program doesn't execute itself. It's the computer that brings it to life, that performs the dance of execution. The computer reads the inputs, evaluates the Boolean function, and outputs the sum. It's the computer that breathes life into our logical blueprint, that transforms our logical specifications into tangible results. That's the execution process in a nutshell. However, you may wonder what exactly is happening inside the computer during each step. Let's delve into the computer's role during each step of a Tau program's execution. The computer is the silent maestro orchestrating the entire process. Its job is to process inputs, evaluate the Boolean function, and generate outputs. At every time step, the computer starts by processing the inputs. It reads the values for X and Y, which are supplied by the user or another part of the system. This is akin to a chef reading a recipe before starting to cook. The computer needs to understand what it's working with before it can proceed. Next comes the logical evaluation. The computer takes the inputs and evaluates the Boolean function f. It's like solving a puzzle or a riddle. The computer needs to find a value for z that satisfies the logical condition imposed by f. Depending on the complexity of the function, this could involve solving a system of Boolean equations or performing a logical inference. Either way, it's a task that requires the computer's full computational power and precision. Once the logical evaluation is complete and a satisfying value for z is found, the computer moves on to the final step: output generation. It's time for the computer to reveal the result of its computation. The computer outputs the value of z, representing the sum of x and y in our example. So to recap, at each time step, the computer processes the inputs, evaluates the Boolean function, and generates the output. It's a cyclical process repeated over and over again, allowing the program to respond dynamically to the input stream over time. Each cycle is like a single beat in the rhythm of the program's execution, and there you have it. That's what the computer is doing at each step of a Tau program's execution. It's a complex process, but when broken down into these steps, it becomes a bit more manageable to understand. Each step is vital, each part of the process is important, and the computer is the powerhouse making it all happen. As we've seen, the computer plays an integral role in executing a Tau program. It's a fascinating process, isn't it? We've journeyed through the process of Tau programming from specification to execution. The Tau language, rooted in Boolean algebras and temporal logic, allows us to draft out a program specification, transform it into a logical formula that Tau can work with, find a satisfying model for the formula, and execute the program based on this model. We started with a program specification, which is essentially a formal description of what the program is supposed to do. Given two input variables, x and y, and an output variable, z, we represented the specification by the formula z equals x plus y, where each variable represents a discrete time step. Afterwards, we transformed this specification into a logical formula compatible with Tau. This involved encoding the arithmetic operation into a Boolean function. For instance, we assumed we have a Boolean function f, x, y, z that correctly represents our addition operation in the context of Boolean algebras. Next, we delved into finding a satisfying model for our formula. Given values for x and y, Tau needs to locate a value for z such that our Boolean function holds true. This process involves a search procedure through the space of possible values of z until a satisfying one is found. At each time step, the program receives inputs for x and y. The Tau system then computes the value for z that makes our Boolean function true. This involves a logical evaluation of the formula based on the current inputs. Once a satisfying value for z is found, it is outputted as the result of the program at that time step. The execution of the Tau program, therefore, is a cycle of receiving inputs, finding satisfying outputs by evaluating the logical formula, and producing these outputs. This process repeats at each time step, allowing the program to respond dynamically to the input stream over time. Let's not forget what the computer does during each step. It reads the input values for x and y at each time step. It then evaluates the Boolean function with the given inputs, searching for a value of z that satisfies the logical condition. This step may involve solving a system of Boolean equations, or performing a logical inference based on the specific structure of the Boolean function. Once a satisfying assignment is found, the computer outputs the value of z, which is the sum of x and y in our example. The key to understanding Tau execution is recognizing that the program behavior is determined by a logical formula, and the computer's task is to find values that satisfy this formula at each time step. That's all for today. We hope you've gained an understanding of Tau programming and its execution process. Stay curious and keep exploring.